Hello students, so today's question here says a particle slides on the surface of a fixed smooth sphere starting from the topmost point. Find the angle rotated by the radius through the particle when it leaves contact with the sphere. Let's understand the situation. Here is the figure given to you. This is the big sphere which is fixed in its place. Now the sphere being fixed has an importance because we don't have to deal with the motion of the sphere, then we just have to focus on the motion of the particle, right? As the particle, which is right now at the position A, slides down and reaches the position B. Understand that as this particle starts from rest and move under the effect of gravity down to a position B somewhere, here we are assuming that it is the position B where it leaves contact with the sphere, let's say. Do we understand that as the particle moves down from A to B, it will gain some velocity at the expense of the potential energy that it will lose, isn't it? Because right now initially the particle is at some horizontal level, then when it reaches the position B, it will reach here. So there is a height difference between the 2 points, which of course we can find out in terms of r, the radius of the sphere, and if the angle theta that we have assumed to be the angle between the radial directions for the points A and B. Understand that using the law of conservation of energy, we can first find out the velocity acquired by this particle at the point B. Yes, and then after that we can use the force equation. We can use the force equation at the point B to get the condition that the body leaves contact, that is the normal reaction becomes 0, right? So we'll do it step by step. We'll first use the law of conservation of energy to get the velocity, and then the force equation to get the condition for leaving contact. So before we start off with the law of conservation of energy, let's find out the value of h. Do we see that h, the height through which the particle has come down, is this whole length, which is r, and subtracted from that this particular length, which we get after dropping a perpendicular from the position B to the vertical line, which will be nothing but r cos theta. This length here will be r cos theta. So we can write h is equal to r minus r cos theta. Yes, and now if we use the law of conservation of energy between the points A and B, we will get the loss of potential energy from A to B, which will be nothing but mgh, yes, is equal to the gain in kinetic energy. The particle started off from rest, and if it has a speed v at the position B, we can say that the kinetic energy there will be half mv squared. Yes. Now from here we can substitute the value of h, which will be mg into r into 1 minus cos theta, and this is equal to half mv squared. You see that m cancels out in the equation, and this gives us the value of v squared as 2gr into 1 minus cos theta. So we get the value of v from this equation, right? The speed of the particle at the position B. Now let us talk about the force equation, and for this we will just draw the figure once again. Let's say this is the position of the particle where it right now makes an angle theta with the vertical. See that there would be forces including the normal reaction. There will be a force of gravity acting on the particle in the vertically downward direction. Now since we are saying that the particle just loses contact at this point B, normal reaction here will go to 0, so that only mg remains, and because of the speed that this particle has in the tangential direction, there will be a centripetal force required by the particle in the radially inward direction towards the point O, which will now be provided by the component of mg towards the radial direction, which is nothing but mg cos theta here. This component is mg cos theta. So when we try to write the force equation in the radial direction at the point B, it will be nothing but mg cos theta, providing all the necessary centripetal force, which is mass into the centripetal acceleration at the point B, which will be nothing but v squared by r, isn't it? And now we can use this value of v, substitute it here and solve for the value of theta. Let's do that. This will give us r taken on the other side. It will become gr cos theta is equal to v squared, whose value is now 2 gr into 1 minus cos theta, isn't it? When we solve this equation, gr cancels out first. We'll have cos theta on the left side and 2 cos theta on the right side. So, we'll bring it here to get 3 cos theta is equal to 2, or cos theta is equal to 2 by 3. And this gives us theta is equal to cos inverse of 2 by 3. And this is what we were supposed to find out. Find the angle rotated by the radius through the particle when it leaves contact. This is the angle. Theta is equal to cos inverse of 2 by 3 is the answer.